All right, one more example for these optimization problems. So in this one, we're going to find the point on the parabola, y squared equal to 2x, that is closest to the point 1 comma 4. All right, so there's a little bit of equations to go on here, but let's investigate what's going on. So we've graphed our parabola, y squared equal to 2x. It's opening to the right because it's y squared instead of the usual kind of x squared. So it opens up on its side. We've plotted the point 1 comma 4. So we kind of have our diagram already. And what we're trying to do is we're trying to find the point out of all these points that are on this parabola. There's a whole bunch of points here. We want to find the one that's closest to this point right here. So conceivably, if we're looking, if we're going to eyeball it, we're going to kind of guess, maybe this is the point. But, maybe if I scooch this over a little bit, maybe this point right here is the largest. So this is, whenever we visually just do something, it's an estimate. But what we're trying to do is we're trying to find this point x comma y. That's somewhere on this parabola. That's as close as we can get to this point right here, 1 comma 4. And so first step for these optimization problems, we want to figure out what is our objective function and what is the constraint. Now the constraint, this puts some restriction on what we can pick on x and y. So the restriction here comes in the form of, I can't just go around and pick any point in the plane. I have to pick a point that's somewhere on this parabola. So the constraint here, or the restriction, is that point x comma y has to be on this parabola. And so it has to be on that y squared equal to 2x on that parabola. And so that's going to be my constraint equation. Y squared must be equal to 2x. So when we see these equations like this, really what this is saying is it's saying all the points in the plane, when we graph the parabola, we're saying these are all the points that satisfy this relationship, and they give us this parabolic shape. So if I were to pick any point on this parabola, I know if I take its x-coordinate, multiply it by 2, and I square the y-coordinate, those two values should be the same. And so if we're picking a point, we're kind of being forced here. We have to pick a point on this parabola, and so the x and y coordinates have to satisfy this relationship. It's the constraints, putting some restriction on what x and y can be. All right, so if that's the constraint, what's the objective? Well, this is what we want to maximize or minimize. So we're looking for things with that kind of language. And we're seeing that right here. We want to find the closest point. So we're trying to maximize, or in this case, minimize the distance. So how do we measure the separation of 2 points on the plane? With distance. So that's what we're trying to do here. We're trying to minimize distance. So that's going to be our objective function. All right, so what's the distance formula? How do we find the distance of 2 points? So let's call this capital D for distance. And it's kind of related to the Pythagorean theorem in some way. So it's the square root of, if we have 2 points, what's the distance between those 2 points? Well, we calculate the difference between our x-coordinates, so x minus 1, and then we square it. We calculate the difference between our y-coordinates, so y minus 4, and then we square that. And then we add those two results, and that's all underneath a square root. So this is kind of related to Pythagorean theorem, kind of related to the equation of a circle, but this is the distance formula. So it's the square root of x, the x coordinates, the difference of the x coordinates squared plus the difference of the y coordinates squared for our 2 points. All right, so we have our diagram set up. We've identified the objective and constraint equations. Now we start going through the process here. And so we want to start with our constraint equation, and we want to solve it for either x or y. And so when we do this, we have some choice. Pick whichever one is easier to work with. And in this case, if I wanted to solve for y, I'd have to do the square root of both sides. I mean, that's okay, but if we can avoid doing square root, it's probably better. X is much easier to solve for. So that's what I'm going to do. I'm going to solve this for x. All I have to do to solve for x, just divide by 2. I can divide by 2 all I want. No big issue. Square roots, these start running into some possible issues, so you got to be careful. So solving for x, that's step 2. And what do we get? We get x is equal to y squared over 2. And actually, I'm going to write this as 1/2 times y squared. All right, so there's my x. And then once I've actually solved for the variable, I'm going to take this and I'm going to plug it right into my objective. And that's step 3. We're going to plug that in. And so what do we do? What do we get when we do that? Well, I'm going to get d is equal to the square root. And I'm just going to replace this x here with 1/2 y squared. So I'm going to have 1/2 y squared minus 1 squared plus y minus 4 squared. And there we go. We identified our objective and constraint equations. We solved our constraint equation for one of the variables. In this case, it was easier to do x. We took that result, plugged it into our objective, and now we have this equation here, this function here, which is one variable. So one variable function. All right, so now this is where the calculus starts to come in. And what we want to do is we want to maximize this function. We want to optimize this. So we want to find the y value or y values where this function has its smallest or largest or smallest values. We want to find the critical numbers for this function. So that's what we want to do. We want to optimize this function. And we can do it. We know how to do calculus. That's what we're here for. So what are we going to do? We're going to differentiate, find the critical numbers, and then we're going to test those critical numbers to see if we have a max or a min. Now, this function here, we have all of our derivative techniques at our disposal. Let's get to it. So there's an easy way to do this and a hard way. We're going to do the hard way. And then we'll come back and maybe talk a little bit about the easier way. So step 4, we're going to optimize. So our function here, let's write it out, is the distance function. And we said it was the square root, and we know we're going to be differentiating, so let's get rid of the square root now. And let's write this with raised to the power 1/2. And so we're going to have 1/2 y squared minus 1 squared plus y minus 4 squared, all raised to the 1/2 power. I might regret this. There's an easier way, which we'll talk about. But we're just going to go through, just kind of brute force this, and we're going to differentiate. So let's calculate our derivative. So first part of optimization here is critical numbers. So that means we need to figure out our derivative. So this is chain rule. We're going to be doing some chain rule, a couple chain rules actually. So let's bring the 1/2 down, put it in front. Keep everything inside the parentheses exactly the same. Okay. Subtract 1 from the exponent, so we get negative 1/2. And then we're going to take the inner function here, and it might be a little... We're going to take this inner function, and we're going to multiply by its derivative. That's chain rule. So our inner function is 1/2 y squared minus 1 squared plus y minus 4 squared. That's our inner function. We're going to multiply by that derivative. All right. We got to keep differentiating. So we gotta differentiate these pieces. And while we're at it, we have a negative exponent. Let's write that as a fraction. So instead of raised to the negative 1/2, we're going to make this into a fraction. So this first part, we're done differentiating here. This is going to become 1 over 2 times the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. So I'm just rewriting this back as a fraction. It's sometimes helpful for finding then the critical numbers. Let's differentiate this. So what are we going to get? Well, this piece here we have to use chain rule for both of these. These are both power functions, and then there's some other stuff inside. So if we use chain rule for this first one, I bring down the 2, keep the inner function exactly the same, and then I multiply, subtract 1 from the exponent, gives me 1. And then I multiply by the derivative of what's inside. So the inner function here is 1/2 y squared minus 1. So I'm going to multiply by that derivative. And then I do the same thing for the other term here. So plus, bring the 2 down, keep what I have inside exactly the same, subtract 1 from the exponent, so that just takes me down to 1. And then multiply by the derivative of y minus 4, the inner function. So there's a couple different chain rules going on here. Now if we differentiate this piece, derivative of y squared is 2y, but when I multiply with the 1/2, it's just going to give me y. So this derivative is going to give me y, and this derivative is going to give me a 1. That doesn't look like a 1. A 1. So when I simplify this, I'm just getting a y from here and a 1 from here. So let's write in now our full derivative. And I'm going to take all of this. So all of this actually is going to go onto the numerator because we're multiplying. And while we go, I'm going to simplify things out. So like this 2, I'm going to bring the 2, distribute it through. So when I do that, I get 2 times 1/2 is just 1, and then a minus 2 over here. So I'm going to have a y squared minus 2, and then I'm going to have this extra y from my chain rule. And then over here, this was just 1, so I'm going to have plus 2y minus 8. And there's going to be some more we can do here. And then this is all over 2 times the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. And then if I keep simplifying here, distribute the y. So this y here can go to the negative 2 and to the y squared. If I simplify, this is going to give me y cubed, and I'm going to have minus 2y plus 2y, so those are just going to cancel. So I'm going to have y cubed minus 8 on the top. All over 2 times this big square root. All right. We're getting there. So right now we're just calculating our derivative. We're simplifying our derivative. Now we're at a point where this is about as simple as we're going to get this. So we want to look for where the derivative is 0 and where the derivative is undefined. And the nice thing about when we have it written as a single fraction like this, when we're interested in where the derivative is 0, the only way a fraction can be 0 is if the numerator is 0. So we're going to take this numerator, we're going to set that equal to 0, and then if we solve that for y, y cubed is equal to 8, and then the cube root of 8 is 2. So we get y is equal to 2 here. And also nice when we have a fraction like this, if we wanted to figure out where is the derivative undefined, well, this is where the denominator is 0. And I'll leave it for you to check. There's actually no solution here. So this thing is never 0. But maybe to see why, why is that never 0? Well, you can set it equal to 0, try solving, and you're going to end up with a quadratic formula that you could use or a quadratic equation that you could use the quadratic formula for, and then you're going to run into a negative under the square root sign. But just kind of more conceptually, if we look at this, the only way two squared terms can add up to 0 is if both of them are equal to 0. So we have this squared term right here. We have this squared term right here. And the only way we can add up two squared terms and get 0 is if they are both 0. So what would make this term 0? The only thing that would do here is y equal to 4. And if I plugged y equal to 4 in over here, I would get 16 divided by 2, 8. Get 8 minus 1, which is 7. That's not 0. So the only thing that would make this term 0 doesn't make this term 0. So, regardless of what's happening, this square root term is going to be positive. And what would make this term 0? Well, y equal to square root 2 would. But if I took square root 2 and plugged it in over here, square root 2 minus 4 is not 0. So when I would square that, I would end up with a positive number. So the only two y values, they don't agree here. So if this term is 0, this term is not going to be, and my square root is going to be positive. If this term is 0, well, this term won't be. It's going to be positive. So again, my square root is going to be positive. So there's no one y value that makes both of these terms 0 at the same time. So this square root is always going to be positive. So it's never, the denominator is never equal to 0. So the derivative here is always defined. All right, so we're finding only one critical number. And so now we found our critical number. There it is, y equal to 2. And now we're ready to actually test it. So that's the next step in our work. Part B of our optimization is to test or classify the critical number. So this is where we use one of our derivative tests. And we have a choice: first derivative test, second derivative test. Now you can see it took a little bit of work to get this first derivative. And if we were going to do the second derivative, we'd have to do some quotient rule. We'd have to do a couple more chain rules. It would take a bit of work. So let's do the first derivative test. So in this case, we're going to do our first derivative test because it's going to be easier. All right, so let's plot our interval for y. So y can be any real number. We found only one critical number, which was y equal to 2. So that kind of splits up our number line into two intervals, and we just want to check what is the sign of d prime on each of these intervals. So first of all, what was y prime? Here it is. Let's see if I can copy this. I don't know if I can get it to the next page. Well, try cheating there. That's what I get. So what did we find for dy? Let's write it out. dy was y cubed. Make sure I don't forget. Y cubed minus 8. Yeah. Over 2 times the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. And I never make my square root signs and fractions large enough. There we go. There's our derivative. And so we're just going to look at these different pieces. So when we do our sign chart, we have y cubed minus 8 on the top. And then we have the square root term on the bottom. We'll do 2 times that square root. And then that'll tell us about d prime. And then that'll give us information about d. And then we can classify our critical number. So let's work with this first interval. Pick a test number. 0 is always a good one. If you can get away with 0, it's always good. So when I plug 0 in, I get 0 minus 8, which is negative 8. So that's negative. When I plug 0 into the square root term, what do I get? I get negative 1 squared, so positive 1. And then negative 4 squared, so positive 16. Positive 1 plus positive 16 is positive 17. It's under the square root, but it's still positive. And then I'm multiplying by a positive 2. So this is positive. So I have a negative number divided by a positive number means my derivative is negative. Now what about on the other side? Over here. Pick a test number. Make it easy. So maybe like we'll do t equals 3. Let's plug it in. When I plug it into the top, when I plug it into this y cubed minus 8, I get 3 cubed minus 8, so 27 minus 8, positive. And then when I plug 3 into the square root term here, I get 9 times 1/2, so 4.5 minus 1 is 3.5, but I square it, so it's positive. And then I plug 3 in here, I get 3 minus 4, which is negative 1, but I square it, so it becomes positive. So I have a positive plus a positive underneath a square root with a positive 2 in front, still positive. So this denominator here, the squared terms are always going to be positive. So the whole thing is going to be positive. The whole square root term is going to be positive. So positive divided by a positive means I have a positive result for d prime. And then when my derivative is negative, it means I'm decreasing. And when my derivative is positive, it means I'm increasing. And so if I had to use the first derivative test, I'm filling in my sign chart. And to help me remember, I'm just going to draw in what the graph might look like for, what is d doing? So it's decreasing. And then at y equals 2, that's where the derivative was 0. So it's going to kind of round out a little bit. And then it's going to start increasing again. And so what's happening there, what the first derivative test says, is we actually have looks like a local min. And that's what the first derivative test says. All right, so we have a local min at y equals 2. And it actually was the only critical number out of all possible y values from minus infinity to positive infinity. This was the only critical number. So because we only found one, not only is this the absolute min, it's the absolute, or not only is this the local min, it's the absolute min. So we have an absolute min at y equals 2 precisely because only one critical number on the interval from minus infinity to infinity. So Only one critical number here, which means we're guaranteed then that this thing is actually an absolute min. And so putting this all together, we've found the y value that gives us the, we've sort of identified the point, but let's actually go back. Make sure we answer the question. So we want to find the point on the parabola that's closest to the point 1, 4. We find the y value where this happens, and we verified that we are actually finding the closest. We did actually minimize the distance function, so we have actually found the point that gives us the kind of the closest location. But the problem is actually asking us to find the point. So that means x comma y. We need the x coordinate. And here we go. So we want to use our constraint. Once we actually know what y is, use the constraint to find x. So we have a couple different equations, but come back to this one where we actually solve for what x is. And so if y was equal to 2, well, plugging that in, we get x is equal to 1/2 times 2 squared. 1/2 times 4 is 2. And, okay, we got kind of lucky here. So we just kind of guessed or estimated visually, and we kind of drew it there at 2, 2. But we have the supporting calculus now. Took a bit of work, but we got there. And let's make sure we answer the question. So that's kind of the last step here. Just make sure you actually answer the question. So it wants us to find the point. So 2, 2 is the closest point on the parabola. All right, so we just want to make sure we're actually answering the question there. That's a good one. That one's fun. Now, I guess I kind of mentioned there's an easier way, and this one's already taken quite a bit of time. But it turns out, instead of optimizing this, the square root of, instead of optimizing the square root of this function, or this entire square root function, what we could have done is optimized just this inner function part. And that's because the square root function is increasing. So we'll kind of make a little note of that right here. Instead, since square root is an increasing function, we could have optimized just what was underneath the square root, and that would have made the derivative quite a bit easier. And then we would have come up with the same result, the same y value. So we could optimize that piece that's just under the square root. So 1/2 y squared minus 1 squared plus y minus 4. And I'm out of space here. So this might be good practice to instead of optimizing this entire thing, call it f of y. And let me write f of y up here. Keep running out of space. It's just the term that's underneath the square root. So 1/2 y squared minus 1 squared plus y minus 4 squared. And why we can just optimize this is because the square root is an increasing function. So if we found the y value that made this as small as possible, well, that same y value is going to make this entire square root function as small as possible. So it might be a good exercise. Try it out. Actually optimize this function instead, and you should come up with y equals 2. And why this works is because the square root function is an increasing function. So if something makes this as small as possible, well then it's going to make that entire square root function as small as possible. Might be a fun thing to try. All right, so that was a good one. And so really that's, again, we're seeing the process here. So all of these optimization problems, once you kind of have the conceptual diagram and understanding of what you're looking for, the process becomes, pretty similar. Identify the objective and constraint equations. That's probably the hardest part. This problem was a little bit more difficult in terms of calculus. Then we actually take our constraint equation, we solve it for one of our variables. We take that result, plug it into the objective. This is things we've been doing in all the examples. That gives us a function that's only one variable here. So now we can actually optimize it. And so what do we do to optimize a function? We look for the critical numbers. So we calculate the derivative. Sometimes it takes a little bit of work. We look for where the derivative is 0, where the derivative is undefined. And then once we have our critical numbers, so this is our critical number here, then we need to test it. So first derivative test, second derivative test. Here, because this was such an involved function, first derivative, we didn't really want to do any more derivatives. So first derivative test was kind of the way to go. We do our sign chart and then use that to help us classify. And we saw that it was a local min. In a lot of these problems, we're only getting one critical number. So not only is it a local min, it's an absolute min in this case. And then last step is just make sure we answer the question. All right, so yeah, that's a good one. That one, the calculus was a little bit harder because we had the complicated derivatives and whatnot. But all right, so that's going to do it. And I think we're going to end with one more little discussion. So we'll see you there. And that's just about some of the common geometric formula that we sometimes see in these optimization problems. So that'll be a quick one. We'll see you there.